which occurs in some range of speeds. For our second experiment, the wind tunnel has been arranged with two identical nozzles discharging air from the settling chamber to the atmosphere. In this way, we get two air jets of the same diameter and with exactly the same airspeed. Our purpose now is not to measure the drag itself, but only to compare the drags of two objects at exactly the same airspeed. The two objects are mounted on the equal arm balance. We may then see which has the greater drag and which the lesser drag merely by observing the deflection of the balance. In this experiment, we are going to mount on the balance arm two balls of exactly the same diameter. From a distance, they look nearly alike, but they differ in a small yet all-important detail. One of them is very, very smooth. The other has on it some scratches, very fine scratches, together with this narrow strip of thin plastic tape. Observing these very slight differences in surface geometry, you would hardly expect that this could make very much difference to the airflow or to the drag. I'm now adjusting this pendulum weight so that the lever arm will be horizontal when there is no airflow. We're ready to begin the experiment now with a roughened ball near me and a smooth ball on the far side. You see that the speed begins at 30 miles per hour, and the deflection of the balance beam indicates that the smooth ball has less drag, as you might possibly expect. Now I'm going to increase the speed, and as I do, the beam deflects still further, but the smooth ball has less drag all the time as the speed goes up to 75 miles per hour, 100 miles per hour, approaching 125, but there she turns over, and now you see that the smooth ball has more drag, indicating some sort of reversal in the flow pattern. This is very puzzling, and I'd like to do the experiment once more, so I'm going to reduce the airspeed. Now the speed is down again to about 60 miles per hour. I'm going to increase the airspeed steadily up to about 150 miles per hour while you watch the balance beam to see which ball has the more drag. Well, we would hardly have predicted that, would we? As a matter of fact, not only is the drag of the rough ball sometimes less than that of the smooth ball, but if we had made measurements of the drags of the two balls using the weighing scale, we would have found that at some speeds, the drag of the rough ball is only 1/5 the drag of the smooth ball. This certainly seems like a great deal when we consider how little different the two balls are. Surely we will have to turn to some fundamental ideas in fluid mechanics in order to understand why this is so, how such a very small cause as a slight roughening can produce such a very large effect as a 5-fold reduction in drag. Next we are going to do two related experiments, one in air, which has only a small viscosity, and one in glycerin, which has a very large viscosity. We begin with the air experiment. The wind tunnel is still arranged with the two nozzles and with the equal arm balance. One of the two objects whose drags we are going to compare is the smooth ball that we have just tested. The other is this streamlined shape. We might call it a bomb. Later we shall discuss more precisely just what we mean when we say streamlined. For the moment, the important point is that the maximum diameter of the bomb is precisely the same as the diameter of the ball. The difference between the two is that the shape of the bomb is more or less like a teardrop. There, we're ready now. We brought the speed up to about 30 miles per hour, and you see that there's a slight deflection of the balance arm, indicating that the bomb has slightly less drag at this speed. Now we increase the speed. We've gone up to about 50 miles per hour. You see that the difference in drag is even greater. Here we are at 75 miles per hour, 100 miles per hour. The bomb still has less drag. 125 miles per hour, 150 miles per hour. And as a matter of fact, we could have gone up in speed as high as we liked, and still the bomb would have had less drag. For the second of our pair of related experiments, we use these two tubes containing the same viscous liquid, glycerin. I am going to drop two models simultaneously, one in each tube, to see which goes faster. Here are the two models. You see that they are small-scale replicas of the models used in the wind tunnel experiments. One of them is a smooth spherical ball. The other is a bomb shape having exactly the same maximum diameter as the ball. In the wind tunnel, the two models were mounted on an equal arm balance in such a way that they had the same net weight in air, the fluid in which their drags were being compared. These models also have air, but in glycerin, the liquid in which they are to move. In the wind tunnel experiments, we compared the drags of the two bodies at the same speed. In the liquid, however, we shall compare the speeds of the two objects when each has exactly the same drag. Now, when we drop an object like this steel ball into a liquid, it at first accelerates. But as it moves faster, the drag on it increases, until after some time it moves at virtually constant speed. This ultimate speed is called the terminal speed. Here is a stroboscopic photograph we made a short while ago. The time interval between exposures is constant, and so the distance between successive positions is a measure of the speed at successive instants. You see that there is a zone of acceleration which gradually merges into a range of constant speed. Now, and this is important, when an object moves uniformly at terminal speed, the sum of the forces acting on it must be exactly zero. At terminal speed, therefore, the drag acting on the object must exactly counterbalance and be precisely equal to the net weight. You see that the two models do have exactly the same net weight in glycerin. And so they have exactly the same drag when each moves at its own terminal speed. If the terminal speed of one is greater than that of the other, it offers less resistance to the flow. Now let us recall that in the wind tunnel experiment, the streamlined body offered less resistance to the airflow. At the same speed, it had less drag. The question now is, will it also offer less resistance to this viscous liquid? For the same drag, will it have more speed? They're already at terminal speed. Since these are plastic models, they drop much more slowly than the steel ball we dropped a moment ago. The answer to our question is no. For the same drag, the streamlined body has less speed. Conversely, if we were to make experiments at the same speed, we would